So myself, Dr. Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the topic name is EPR, Electron Paramagnetic Resonance and Spectral Properties of Chromium 3+ ions in borate classes. So last and previous session was we discussed about the experimental techniques of the electroparamagnetic resonance EPR studies, optical observation spectrometer, excitation, emission and decay time measurements, X-ray diffraction profile and Raman spectrometer. These are last session we discussed about the topics. Today I am going to discuss about the EPR and spectral properties of chromium 3+ ions in borate glasses. Outline of the today talk is introduction and evidence of mixed alkali effect, next experimental methods, result and discussion. Finally, we have conclusion or summary of the today talk. So, main introduction. Glass is one of the most important material in modern information and communication and laser technologies. The drastical moving market for television screens and data displays needs glass with a variety of coating on its surface. So whenever glass is one of the most important material in modern communication, at the same time it will be useful for the different kind of applications. TV screens and data display need glasses with a variety of coatings on its surface by using the glass material. Next, glass is extremely stable against environmental attacks. So glass is generally extremely stable against environmental attacks. Glasses are roughly speaking liquids that do not crystallize even at low temperature. That means, if you roughly speaking, glasses is liquids that do not crystallize even at a very low temperature also. It does not cool down time also. It cannot at low temperature also. It cannot crystallize. That is the glass nature. So glasses are very versatile material due to the fact that they can be easily doped with transition metals or rare earth ions. Transition metal means chromium 3+, magnesium 3+, and iron 3+. These are the transition metal ions. And in the case of rare earth metals, samarium, dysprosium, erbium, terbium, yttrium, there are different kind of rare earth metals. Whenever doped with the transition metals or rare earth ions, we can change the different kind of glass properties we can study by using the glass systems. Next, main introduction of the borate glasses. So in our study, EPR and spectral properties of chromium 3+ ions in borate glasses. So particularly we know to discuss about the main introduction of the borate glasses. So borate glasses are particularly interesting model system as they exhibit a variety of structural changes with alkali content. That is very important. Alkali content. Borate glasses is a promising host for incorporation of chromium 3+ ions. Here doped with chromium borate glasses and added with a mixed alkali elements. So alkali elements we are using for lithium, sodium, potassium, cesium, rubidium. These are the different kind of alkali elements. Whenever borate glass is the glass former B2O3. So in a glass former B2O3, we are adding with some mixed alkali elements, lithium oxide and cesium oxide, CS2, cesium oxide, and doped with chromium 3+ ions. Chromium 3+ ions. These are the main host material in this glass system. So we are using borate glasses that is added with alkali elements, lithium oxide and cesium oxide, and doped with chromium 3+ ions. So chromium 3+ doped borate glasses are also of interest in this context because the emission band is much broader than the ionic crystal. If you compare to crystal structure, if you are doped with the chromium 3+ ions in glass materials, it can exhibit the emission band. Emission band is much broader than the ionic crystal. So we can get the emission band in the region of red region. We can get broad emission whenever chromium 3+ ion doped with borate glasses. So that is one of the much important application. The optical properties of chromium 3+ ions are modified by the random disorder structural glasses because the environment of each chromium 3+ ion in the glass varies as a consequence of differences in bonding to nearest neighboring ions. So these are the one of the important optical properties whenever doping with chromium 3+ ion are modified by the random disorder structure of the glass. It will change the randomly disorder structure because the environmental of each chromium triplet ion in the glass varies as a consequence of differences in bonding of nearest neighboring ions. So neighboring ions, that means compared to ligands. So whenever chromium Cr2O3, so chromium oxide is automatically in ligand ions, that means oxide ions will be takes place in the environmental change, that is in the optical properties. So this results in a site-to-site differences in the energy level structure and in the radiative and non-radiative transition properties of chromium triplet ions in the glasses. That is very important in the borate glasses. So these are the important introduction on the borate glasses. Next, coming to the second one is the an evidence of mixed alkali effect. So here alkali effect. Alkali means alkali contents. That means lithium. Alkali elements is lithium, sodium, potassium, cesium, rubidium. These are the alkali elements in the periodic table. So by using these alkali elements, we are going to dope with the chromium triplet ions. How structure studies changes in the borate glasses, that we are going to study in the by using the EPR and optical and luminescence properties. So the mixed alkali effect is not much studied in the borate glasses. So in the previous years, they are not much studied in the borate glass in the effect of mixed alkali effect. So now we are going to study the mixed alkali effect in the borate glasses. So borate glasses are particularly good model system as they exhibit a variety of structural changes with alkali content. Whenever added with a alkali content, at that time it will exhibit the variety of structural changes in the alkali content. So what are the alkali contents? So among the transition metal ions, chromium triplet ions is interesting for spectroscopic investigation due to its favorable absorption and emission properties when incorporated at octahedral site of the host matrix. Whenever chromium triplet ions doped with the borate glasses, so this chromium triplet ion is one of the transition metal ion. So that means doped with the borate glass, we can change the interesting study of the spectroscopic analysis. So optical and luminescence properties we can study the by using of chromium triplet doped borate glasses. Moreover, in recent years, investigations on electro-paramagnetic resonance (EPR) electron paramagnetic resonance (EPR or ESR) electron spin resonance. Both are similar because here electro-paramagnetic resonance, optical absorption, and luminescence spectroscopy of chromium triplet ions in a variety of inorganic classes have been made due to their technological importance in the development of tunable solid-state lasers and luminescence materials. So this is the main application by using the EPR studies, absorption, optical absorption, and luminescence. These are the spectral properties. Whenever chromium triplet doped with the borate glasses, we can use these glasses in the application or development of tunable solid-state lasers. At the same time, luminescence materials, because whenever borate glasses doped with chromium triplet ions, it exhibit red emission, broad red emission. That means we can tune the different kind of energy levels by using the that is why this is mainly useful for the tunable solid-state laser applications we are using for the chromium triplet doped borate glasses. These are the one of the important applications in the chromium doped borate glasses. Next, coming to the how to select the material selection. Though in the present section highlights the facts or advantages behind the selection of borate glass system for the present study. In this study, we are going to study the EPR, that means electron paramagnetic resonance, at the same time optical absorption and photoluminescence studies of chromium triplet ions. In lithium oxide, cesium, here mixed alkali content we are taking lithium oxide and cesium oxide. These are the mixed alkali elements, and glass former is B2O3. So glasses an evidence of mixed alkali effect. Here we are studying the mixed alkali effect because we are adding the lithium oxide at the same time cesium oxide. So variation of lithium oxide and cesium oxide, we are doped with the borate glasses. At the same time, transition metal chromium triplet ions we are doping. So this is the glass composition of the present borate glasses. That is the composition. There is the chemical composition of the borate glass system. First we are taking lithium oxide X lithium oxide and 30 minus X cesium oxide and 69.25 B2O3 and 0.7. This is a dopant concentration you are taking 0.75 mole percentage. So this is the mixed alkali element. The lithium and cesium content should be we are varying the mixed alkali elements only. Borate glass and chromium ions concentration will be fixed. We are changing or varying the lithium oxide and cesium oxide. So Mixed alkali content only we are varying. That is in the composition is the 5 equal less than equal to x or less than equal to 25. So 5 mole percent to 25 mole percent of the lithium oxide and cesium oxide we are varying in the borate glass system. So how we are going to study the borate glasses? So this is the experimental technique methods or preparation of borate glass systems. So first initially we have to take the above mentioned chemical composition. In this borate glasses we are taking lithium oxide, cesium oxide, B2O3, boron trioxide and chromium oxide. Dopant is 0.75 mole percentage. So that chemical composition we are taking the all the composition in the weight percentage of the 8 to 30 grams of the weight we are taking the and measure the optical balance, and we have to take from weight is 80 to 8 gram to 30 grams. After taking the chemicals we are put into the platinum crucible. We have to use some platinum crucible. We keep in platinum crucible, and after we are using this technique is a melt quenching technique. We are preparing this borate glasses by using the melt quenching technique. So at that time we are using the electrical furnace. At the temperature of borate glasses we have to use the temperature in between 850 degrees centigrade to 1000 degrees centigrade. In between we have to keep the borate glass chemical composition in the platinum crucible. We are keep into the electrical furnace. After heating the temperature, so up to reach the 850 or 900 degrees centigrade, we can kept at the temperature of 900 degrees centigrade for 1 hour. So after 1 hour, it will be melt. It will form the solid material to liquid state. After melting the glass composition, we have pour into the preheated brass mold. This is the preheated brass mold. After heating the glass composition, we have to pour into the preheated brass mold. So after pouring into the brass mold, it will be form as the glassy state. That means we have to annealing. After that, we have to annealing at the temperature of below the glass transition temperature. That is in the borate glasses, the glass transition temperature is below the glass transition temperature. That means around the temperature of 300 degrees centigrade. We have to annealing. So annealing means mainly purpose of the annealing is mainly to avoid the thermal stress and strain. Then only it cannot break, it cannot have any disorder structure in the glassy system. So that is why we are going to keep in the annealing at the temperature of below the glass temperature. That is in the case of borate glasses 300 degrees centigrade. After taking the samples, we have to polish and cut the pieces, different kind of small pieces for optical and luminescence measurements. So first initially we have to measure the XRD profile, because we have to know after preparation of the glass system, we have to whether it is a glassy nature or crystalline nature. We need to find out first step. So that is why we have to take the glass sample, crush into the fine powder, then you send to XRD measurements. In XRD measurements, we can know it is a glassy nature or crystalline nature. So in this profile, you can see here, this is a complete each and every peak is broad. We cannot get any sharp peaks. If you are getting like this sharp peaks means that looks like a crystalline nature. But in our case, this is a broad peaks you are observing. That means it is completely exhibit the glassy nature. So our preparation glass is completely glassy system. So after taking the glass material, we are sending for different kind of measurements, spectral measurements. That is optical observation, EPR studies, next luminescence studies. That we are going to study by using different kind of techniques. So experimental technique are methods for calibration purpose. First one is EPR, electron paramagnetic resonance spectra. So that first we are going to study the electron paramagnetic resonance. So that by using the system is electron paramagnetic resonance EPR spectra of the sample were taken at GL Fe1x ESR spectrometer with the X-band frequency. We are using the X-band frequency. That frequency is microwave frequency. X-band is 8.8 to 9.6 gigahertz. That is, we are using the microwave frequency from 8.8 to 9.6 gigahertz. This is the X-band ESR spectrometer with a field modulation of 100 kilohertz. So field modulation also very important while measuring the ESR spectrometer. So that is the ESR spectrometer. Then we are going to measure the optical absorption spectrometer. So by using the optical absorption spectrometer, we are using the instrument name is Flickr spectrometer lambda 950. In the wavelength range from 250 to 2500 nanometer. We are spectral range. We are scanning the absorption spectra from starting from 250 nanometer to 2500 nanometer in the case of optical absorption spectra. After that, we can going to measure the fluorescence or emission spectrometer and decay time measurements. So in this chromium 3 plus science, we are measuring the only fluorescence measurements, this emission measurements. So here emission measurements we are using for the Jobin via fluorolog 3 spectrophlorimeter using as a xenon arc lamp as a radiation source. We are using the excitation purpose. We are using xenon arc lamp. This is exhibit the different kind of excitations. So that is radiation source. We are using the xenon arc lamp in the measurement of fluorescence measurements. So in this measurement, we can get the emission data of the Borate classes. So first in the resultant discussion. So first we are discussing chemical composition. Next, how we are prepare the class sample. Then we are measure the optical measurements and EPR measurements. First, we have to discuss about the first measurement, the EPR, electron pyramidal resonance spectra at room temperature as well as low temperature. By first spectra source, the EPR spectra of 0.75 mole percentage of chromium 3 plus dope, lithium, cesium, borate gas at room temperature. See here, this is the x-axis your magnetic field gas. Y-axis is first derivative absorption curve. So we are measuring the in the EPR analysis, we are getting the different kind of magnetic field versus first derivative absorption curve. So here absorption peaks we are getting at the varying of the magnetic field gas. We are varying the magnetic field gas is from 0 to 5000 gas. So here fixing the X band, here microwave frequency we are fixing. We are tuning the magnetic field in the value of gas from 0 to 5000 gas. Otherwise 500 Tesla. This is converted into Tesla. So we can measure the magnetic field should be in gas. Otherwise Tesla. So here see the different kind of composition. So here mixed alkali content. The X equal 5 mole percentage, X equal 7.5, X equal 10, 15, 20, 25. These are the different kind of variation of the alkali content. That means lithium or cesium. So these are the lithium content. So X equal 5 mole percentage of lithium oxide, 7.5 percentage of lithium oxide, 10% of lithium oxide, and 15% of remaining is cesium oxide. So in the case of first case, 5% X equal 5. That means 5% of lithium oxide plus 25% of cesium oxide, CS2. So in the case of 7.5, here 7.5 lithium oxide, remaining 22.5 of cesium oxide. In the case of 10% of lithium oxide, and remaining is 20% of cesium oxide. So these are the varying of the alkali contents. So in that way, we are taking the chemical composition. We are studying the EPR analysis. So here taking it first X equal 5, we are getting the broad peak, and here small hump, small peak, and we are getting broad peak, and here one peak we are getting. So these are the G factor. That means resonance fact signals. We can say this is EPR signal, ESR spectrometer or EPR spectrometer. We can say the G is the Landis splitting factor. That is G value at the low magnetic field side is G equal 4.82 and G equal 4.12 and G equal 1.99 and the other one is G equal 1.97. So this is the mainly this G equal 4.12. This is mainly due to the iron 3 plus content. Inside the borate classes, we can get the iron impurities also. This is a without unknowingly we are inside the chemical only we can get the iron content. That is, but we are doped only chromium 3 plus ions. So chromium 3 plus peaks are the G value is called 4.82 at the same resonance signal G equal 1.99 and G equal 1.97. 97 is a chromium 5 plus. These are the G equal 4.82, G equal 1.9. These are the mainly due to the chromium 3 plus ions. These are the main important peaks in the chromium dope borate class system. At the same way, we are studying the same EPR analysis. We are studying for the low temperature also. So different kind of temperature. Low temperature means 133 K to 163 K, 193 up to 295 K. So low temperature purpose we are using the liquid nitrogen. So liquid nitrogen we have to use, then only we can reduce the temperature from room temperature to low temperature starting from 133 Kelvin to 295 Kelvin at room temperature. We are studying the room temperature ESR or EPR analysis spectra of the chromium doped borate class. Here also same At what you are getting the room temperature, that kind of peaks only were observed in the low temperature also. But resonance peaks looks very systematically in order wise. We are getting G equal 4.82, G equal 4.12, and here G equal 1.98 and G equal 1.97. So G equal 4.82 and G equal 1.99 resonance signals mainly attributed to the chromium 3 plus ions, and G equal 4.12 is mainly due to the impurity of iron 3 plus ion. And the same way, additionally, we are getting one more peak also, that is G equal to 1.97. That is mainly due to chromium 5 plus ion state. So generally in chromium 3 plus Cr2O3 we are doped. We are getting the chromium 3 plus resonance peaks at G equal low magnetic field resonance signal, G equal 4.8 to higher side, G equal 1.99. At the same time, additionally, we are getting two more peaks. That is, one is mainly due to the iron impurity, iron 3 plus, at the resonance signal G equal 4.12. One more peak is G equal 1.97. That is mainly due to the chromium 5 plus. So mainly EPR or ESR signal mainly we study the outer orbital state of the each and every transition metal ions. So we have studied the chromium 3 plus ions in the 3 plus state or 5 plus states. So we can observe the chromium 3 plus ions in attributed to chromium 3 plus state. At the same time, additionally, we are getting chromium 5 plus state also. So that is mainly we can give the these results from the EPR spectra. We can analyze the by using the ESR spectrometer. So next EPR analysis. In this study, the EPR spectra of investigated lithium, cesium, borate glasses doped with chromium 3 plus glass exhibit resonance signals at, that is G is Landau splitting factor, G equal 4.82 and G equal 1.99. The low magnetic field resonance signal with an effective G value at G equal 4.82 is typically for isolated chromium 3 plus ion rhombic sites subject to a strong crystal field effects. So that is a very important thing of the at G equal 4.8 mainly due to the chromium 3 plus ion. That site symmetry is rhombic site. The second point is the resonance signal with effective G value at G equal 1.99 arises due to the contribution from the both the exchange couple of chromium 3 plus ion pairs. This is a very important signal in the chromium 3 plus ions. So exchange couple of chromium 3 plus to chromium 3 plus ion pairs in the case of isolated chromium 3 plus ions. That is the at G equal 1.99. That is the mainly contribution of the chromium 3 plus ion. Next, in additionally, we are getting two more resonance signals. That is the observed the resonance signal with the effective G value at G equal 4.12. That is attributed to iron 3 plus ions present as the unwanted impurity. That is, we are not doped with borate glass in chromium 3 plus only, but in the case of additionally unknowingly here that is unwanted impurity is present in the borate glasses whenever doping with chromium 3 plus ions. That is the G equal 4.12. Next other one is G equal to 1.97. That is mainly due to the chromium 5 plus ions. So this analysis we are getting this data from the EPR analysis. Next, coming to the by using the EPR analysis data, we can calculate the number of spins participating in the resonance. That is a very important formula. In this formula, we need to get the number of spins. How many spins is participated in the EPR signal. So this is a number of spins participating in the resonance N that we are going to find out by using this formula. See here, the number of spins participating in resonance can be calculated by comparing the area under the absorption curve. That means we are getting this kind of EPR peaks. By using these peaks, we can calculate the area under the each and every absorption peak. We can get the area. By using the area under the absorption peak, we are calculating by using this formula. We can calculate the number of spins participated in the resonance signal. That means here comparing the area under the absorption curve with the that of standard. Here we need to get sample value at the same time standard value. That means reference value. Reference we are using copper sulfate 5H2O in the study. At the same time, in sample is chromium 3 plus ions. So we are taking chromium 3 plus ion in the sample present study. Reference or standard value is copper sulfate CuSO4 5H2O in the study. That is of known concentration. This is the reference sample. Present study sample is chromium 3 plus ions. See here, AX scan X whole square base. So AX X represents the our present study sample. Standard means reference values. That value we can get both values. We can compare both values and by apply by using this formula, we can get the here A means area under the absorption curve. Scan means magnetic field corresponding to the unit length of the chart. While measuring the ESR signal, we can note down the scan value. That scan value gives the at the same time sample value. At the same time, we can get the reference value, that is standard sample value. That value we can note down. After G value, capital G is gain of the sample value, at the same time reference value. BM is the magnetic field width, that also sample value, at the same time reference or standard sample value BM, that is modulation field width. Next P is the power of the microwave source. So how much power by using the microwave, that means 9.8 gigahertz you are using microwave frequency while measuring the ESR analysis. At that, how much power you are using in the sample, at the same time standard reference value also you have to note down. By using this all values, we can substitute in this formula, we can get the number of spins participating in the resonance. That value we are studying this is the variation of number of spins with alkali content. See here, x-axis composition, different alkali content composition. 5 mole percent of lithium oxide, 10 mole percent of lithium oxide, 15 mole percent of lithium oxide, and 20 mole of lithium oxide, and 25 mole of lithium oxide. Remaining is cesium oxide. So here 25 mole percentage of lithium oxide, 5 mole percentage of cesium oxide. So you completely you are taking 30 mole percentage. So that you are varying alkali content. Then that is why you are studying the mixed alkali effect. That is why you are taking x-axis composition versus y-axis number of spins. That is NS. By using the above formula, you can calculate it. No, that value we are using to that graph you are plotting. So composition, lithium content, at the same time number of oscillations. So initially that value shows similarly low value, and again decreasing, again increasing, again decreasing, again increasing. So this effect shows the mixed alkali effect. That means whenever borate glasses doped with alkali content, it shows this whenever composition versus number of spins, we can shows it shows the randomly increasing, decreasing, increasing, randomly it shows the difference. This variation may be due to the structural changes with composition and also the modification of boron network with alkali content. This is mainly these changes you are observing now, increasing, decreasing, increasing, again increasing. So this is mainly due to the structural changes with the composition and also the modification of boron network with alkali content. This is one of the important phenomena we are studying the mixed alkali effect by using the chromium 3 plus borate glasses. So again we are going to measure a flat of log n versus 1 by t. That means in x-axis we are measuring the 1 by t temperature, absolute temperature, versus log n means number of spins participated in the resonance signal. So that we are calculating by using the x-axis 1 by t, y-axis log n. So here that values we can fit into the log n equal to 20.86 plus 17.53 by t, that is temperature. So that by using this diagram, we can calculate the activation energy. That is activation energy equal to 0.035 electron volt. So by using this slope, we can calculate the activation energy. By using the activation energy, we can measure the Curie constant also. Curie constant and paramagnetic Curie temperature also. See here, Curie constant C equal to 0.2342 EMU per mole. The paramagnetic Curie temperature theta T equal to minus 48 Kelvin. So by using that low temperature analysis, so we are getting ESR signal at low temperature. So in this spectra, we are getting low temperature and different kind of resonance signal. By using this resonance signal, we are plotting here. So that resonance and versus 1 by t. So by using this plot, we are going to get the activation energy, Curie constant, and paramagnetic Curie temperature. So Curie constant C equal 0.2342 EMU per mole. Next, paramagnetic Curie temperature theta P equal minus 48 Kelvin. So this graph you are getting the activation energy, Curie temperature. So in other graph you are going to temperature versus susceptibility. That means susceptibility also we are going to calculate by using the ESR signal. So in this susceptibility, by using the formula N G square. N is the number of spins participated in the chromium 3 plus, and G is the spectroscopic splitting factor. Beta is the Bohr magneton. J is the orbital quantum number for chromium 3 plus ion. For chromium 3 plus ion, J equal 3 by 2. That value is J equal orbital quantum number J equal 3 by 2. because chromium 3 plus ion you are using as a dopant. So that is why that orbital quantum number J equal for chromium 3 plus ion 3 by 2. Kb is the Boltzmann constant, T is the absolute temperature. By using this formula, we can calculate the susceptibility of the paramagnetic resonance of the chromium 3 plus ion. So in this case, we are going to calculate the susceptibility. As the susceptibility, we are going to calculate the Curie temperature. So these are the two graphs, a plot of log n versus 1 by t and a variation of paramagnetic susceptibility with temperature. So in these two plots, by taking the ESR signal, we are going to get the two important parameters. One is we can calculate the activation energy 0.03 electron-volt. At the same time, paramagnetic Curie temperature also we can calculate by using the ESR signal. So ESR signal, important three parameters we can calculate: number of spins, the number of spins of the resonance signal, one parameter, that is by using this formula, n value, number of spins participating in the resonance signal, that we can calculate. Next, other two parameters is activation energy, and last one is the Curie temperature. So these values we are going to find out by using the ESR signal or EPR signal. Next, coming to the optical absorption and luminescence spectra. So optical absorption spectra, see here, optical absorption spectra, we are getting the 5 mole lithium oxide, low concentration of 5 mole lithium oxide and 25 cesium oxide, 69.25 of borate glasses and 0.75 of chromium. So completely total composition percentage is 100 mole percentage. So we are studying the optical absorption at room temperature only. So in this room temperature, we are getting the three peaks, three not sharp peaks, broad peaks. One is little bit sharp and one more is broad peak. These are the different energy levels bands of the chromium 3 plus ions. Chromium 3 plus ion from ground state to different levels. That is, first one is doublet A1G G state. Other one is a quadrate T1G of F state. Next, other one is a small broad peak is the quadrate T2G of F. So these are the absorption peaks of the chromium 3 plus dope borate glasses. So this is the second graph, is shows the luminance spectrum of the chromium 3 plus ion doped with lithium cesium borate glasses. Here, laser excitation, we are using the Jobiniag spectrophlorimeter. So here, using the excitation wavelength is lambda Ex, that is equal to 483 nanometer. We are using as the excitation pump source. We are using the xenon arc lamp. It will exhibit the excitation source value is 483 nanometer. We are using. So we are getting the WTEG2 quadrate A2G. We are getting the emission in the region of around 650, around nearly 640 to 650 nanometer. We are getting this red emission. So broad red emission you are getting. That is mainly useful for the tunable solid state laser applications. We are using for the chromium 3 plus doped borate glasses. These are the one of the important application while doping the chromium 3 plus ions in borate glass system. This is the important application because we are getting the broadband only. We are observing only one emission peak at the wavelength of the 654 nanometer. That is the energy level attributed to the WTEG2 quadrate A2G. So this is the in the color is the red region. That is the useful for the red emission, red laser applications. We can use for the tunable solid state laser applications. We are using for the chromium 3 plus dope borate glasses. Next, coming to the optical absorption and emission peak, what we are getting the values and transitions, how much nanometer we are getting. So by using above graph only, this data taken from this graphs only. So first is optical absorption spectrum observed at room temperature of the glass sample is shown in figure. The spectrum exhibit one broad band at 60 nanometer and an intense band at 441 nanometer. There is the energy levels, there is centimeter inverse, and a weak band at 391 nanometers. These are mainly the observed bands are characteristics of chromium 3 plus in octahedral symmetry. This shows the absorption spectrum. Shows the this broad bands is mainly observed bands are characteristics of chromium 3 plus ions in octahedral symmetry. The three bands are assigned to the DD transition, that means d orbital transition, D to D transition, because chromium 3 plus ion in the d orbital transition metals are comes from the d orbital. So that means the D to D transition is quadrate A2GF to quadrate 2G. That is first transition. The other one is a quadrate A2GF to quadrate T1GF transition. Next other one is a Cr3 to WA1G transition in the increasing order of energies. These are the we are observing from the absorption spectrum. This is the luminescence spectrum shows the glass sample measured and then using the laser excitation of lambda excitation wavelength is 483 nanometers shown in the figure. That means here in this figure. So this is the luminescence spectrum. That value we are getting the 480 nanometer we are pumping. The luminescence spectrum exhibits a red emission peak observed at 640 nanometer. I don't know 640 nanometer. That energy is 15,625 centimeter inverse, which is assigned to the transition from the upper energy level. That means ground state to excited state. So that upper energy level WTEG to ground state level 48A2G ground state of chromium 3 plus ions. This we are observing for the red emission. So this red emission is mainly useful for the solid state laser applications. We can use for the chromium 3 plus doped borate classes. Next, finally, conclusion or summary of the EPR and spectral properties of chromium 3 plus ions in borate classes. First is the chromium 3 plus doped classes exhibit two resonance signals which are attributed to the isolated chromium 3 plus ions and exchange couple of chromium 3 plus ions. That is the G equal 4.82 and G equal 1.99. These are the very important of the chromium 3 plus. Additionally, also you can get two more peaks. That is one is due to the chromium 5 plus, other one is iron 3 plus. That is unwanted impurity. So main peaks is in chromium 3 plus is G equal 4.82 and G equal 1.99. These are the important ESR signal or EPR signal of the chromium 3 plus doped classes. So this is mainly attributed to the chromium 3 plus ions and exchange coupled chromium 3 plus pairs. So that site symmetry we are going to study in the by measuring the ESR or EPR signal. The second one is the optical absorption spectrometer we have studied. In that one, the optical absorption spectrum exhibits three bands characteristics of chromium 3 plus ions in octahedral symmetry. The three peaks shows the octahedral symmetry nature. So that we are getting from the optical absorption spectrum. Next, from the EPR and optical absorption techniques, one can know the site symmetry and oxidation state of the transmitted line. These are the very important things. So from EPR and optical absorption technique, one can know the site symmetry and oxidation state of the transmitted lines. So we are doping Cr2O3. So we can get the chromium 3 plus states. That is the oxidation state of the transmitted lines. We are going to study by using the EPR at the same time optical absorption spectra also. So that we are going to study by using the EPR and optical absorption spectrometer. So last is the luminescence spectrum exhibit in emission band in the red region, which is assigned to WTEG to, that is excitation level to ground state, Borate A2G transition. This transition is mainly shows the red region, that is 640 nanometer in red region. That is mainly useful for the red laser applications, and also this is we can get the broad emission. That is why you can tunable solid state laser applications also we can use for the chromium 3 plus doped borate classes. These are the very important conclusion for the in this present study EPR and spectral properties of chromium 3 plus ions in borate classes. So these are the references used in the present study. This is a important. So last reference is the one of my papers published in this same study of the EPR and spectral properties of chromium 3 plus ions in borate classes. So these are the cited references. Finally, thank you. So next section to be continued in the next chapter. Thank you once again. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.